hopefully pretty question based, but yeah. I mean, an outcome of this might just be that we take the recording and make some more formalized materials from it even. So,
yeah.
I mean, the white paper's there, but unless I update it every day, it's always a little bit behind.
Yep.
Okay, I think we're recording.
It says we're recording.
Yeah. I'm going to press the other record button here.
Something says live on my screen, but not recording. So that's fun.
It's live on YouTube. Oh, there we go.
Oh, it says recording.
I'm going to do recording as well, just because I don't trust the live thing. Anyway, thanks everyone for joining us. If you're watching on this is IPLD weekly sync, although we're a little bit, we weren't supposed to have one this week. Apparently we've switched to every second week, but we're joined by the good folks at Textile who, and we're going to focus today on threads and possibly a little bit of buckets. So the Textile data structure and a protocol for collections of data and links of things. So we have, there's a bunch of people with technical questions about threads, and we'd love to get these guys giving us some technical background that is deeper than what's easily accessible through the documentation. So I'll hand it over to Carson or Sander and let you guide us through, and we'll pepper you with questions as they come up.
Cool. Yeah. I mean, I think what Sander and I were thinking we might do is start with like pretty high level, like what are threads from a conceptual high level point of view? What sort of problems do they solve? And then after that, dig a bit deeper into like the IPLD structures that we use and like some of the roadblocks that we came into when developing the data structure, and then like why we chose one sort of way of doing things over another. Because even out of that, we may be able to say like, oh, you know, there was a missing codec here and it looks like this, and, you know, maybe we can go out and all build it or something. So if that seems reasonable to you, Sandra, do you want me to just do a quick overview thing and then go from there? Does that seem reasonable? Cool.
Yeah.
So I'm just going to quickly share my screen. This is an image from our Threads white paper, but it's probably the most kind of like useful contextual, like high level overview of what a thread is. So, you know, realistically, we think of threads, plural, as sort of right now two things, which is like threads protocol for data exchange, and then threads database, which is the sort of like practical implementation on top of that. And so today we're going to focus on threads, the protocol and data structure. And so a thread is really just like a topic about a given data set. And it has associated with it a set of single writer logs. And so you may have any number of peers interacting on a given topic, and each of those peers may be contributing updates to essentially the mutation of this single topic data set. And each peer is responsible for their log and their log only, and only they are allowed to write to their given log. And a log is essentially keyed by their peer ID, or the public key of their peer ID. And then the thread as a collection is basically a collection of all these logs and addresses associated with the peers involved in that log and various other metadata, including some keys, which I'll talk about in a second. And then in practical use, you know, if you have multiple peers that are interacting on a given data set, each one may be mutating the state of that data set within their own log. And then some data materializer or materialized view of the final outcome of that, which is basically the folding of updates of that log to produce, or the set of logs to produce the final state, may be rendered or materialized on some client somewhere. The single writer log thing is kind of key, and it gives us a lot of really useful properties. One of the most useful ones is that you can essentially defer materializing that view until the time that it's needed. Because you know that there cannot be any conflicts because only one peer is responsible for their given log. You can deal with, so there's never going to be conflicts on sort of the write side, but there could be conflicts on the read side when you actually try to materialize that view. And so it's up to the peer that's materializing the view to deal with those conflicts when they arise. So this is really nice for distributed systems because you can basically not worry about, like, you can exchange data and then deal with like problems later. And this turns out to be really useful property from where we came from, which is like in the mobile world and like collaborating peers and things like that, where you don't want to waste time or effort trying to deal with conflicts ahead of time. You end up with these crazy branching structures. Instead, you can kind of deal with it on read. And other teams have arrived at similar ideas as well, but yeah, there's some really nice properties here. So that's sort of, and there we can talk about why single writer logs are useful for other things as well, but that's a good high level overview of that. Okay, so a log is keyed by the peer ID. And Sandra, feel free to jump in if I like miss or go over, you know, brush over something really simple, or sorry, really important. But anyway, we've got our logs. Each peer is responsible for writing to them. And a log is essentially a hash-linked append-only log of like IPLD blocks. In fact, it's a hash-linked log of records. We call those sort of higher level thing records. And the records, each one contains what you can kind of see here in this figure, which is it's got like some header information, including the key, or sorry, the time. And we use the term time loosely. That's generally some sort of like, you know, logical clock or something like that to represent time. It need not be wall clock time. And then the key that is used to encrypt the body of that record. So you actually stick the key, it's a randomly generated key each time. That gets stuck in the header. And then that all gets wrapped by an additional key called the read key, which you can see here. And the read key is used to encrypt the body stuck in the header. The key is used to encrypt the body that's stuck in the header. The read key is used to essentially wrap all of that stuff to create a record. And then each record that gets added to this single writer log is additionally wrapped with the replicator key. The reason for this multi-layered sort of way of doing things is that allows a peer to pass, or a group of peers to pass off a replicator. Sorry, it used to be called a replicator key. Now it's called a service key. But anyway, you can pass off that key to a service provider. That service provider can track log updates over time without being able to access the contents of those log records. So they only need to get sort of like one layer deep, so they can follow the hash links, but they can't go any deeper than the read key if they're not given the read key, obviously. And that gives some useful properties because now we can have like trustless service providers on the network that do nothing more than just replicate the thread content, but don't actually contribute directly to like the update or like editing of any actual thread content. And yeah, then that's where the hash linking piece comes in. The bodies themselves can be pretty much any arbitrary data, though in practice these are IPLD blocks. And so in theory, you could have kind of blocks all the way down, and you could have peers that are exchanging like actual IPLD blocks in the body. But this gets wrapped in a read key, and we can talk a bit about that because that was a sort of like design decision that we had to make to deal with encrypted data. But I think that gives you a pretty good overview of the general structure of what a thread really is at the sort of base layer. And then of course the threads protocol defines like how you actually exchange records between peers, you know, and which peers are allowed to do certain things, and like pinning and all that stuff, that the actual exchange of data that needs to happen to make a distributed network work. There's a few interesting things that we've discovered in developing threads. You know, this is designed to be run on a like peer-to-peer basis. Each peer would be running a thread daemon, which sort of just wraps a IPFS light peer for exchanging data and all that good stuff. But in practice, we also find that, people also want multi-tenant systems where you basically have like one thread peer that's actually responsible for other peers' threads. And so that presents like sort of new design decisions that you have to end up making kind of on top of this. And we could talk about that as well, because that's probably in practice the bigger challenge than like coming up with a peer-to-peer protocol. It's like a multi-tenant use of that peer-to-peer protocol that makes things a bit more tricky. Anyway, so I'm going to stop with that high-level overview and pass it off to Sander, who can talk a little bit more about some of the like key design decisions that we made around like the keys and things like that. But also, if there's any questions, now is a good spot to stop.
Yay! I was going to ask if I can jump in. So when you were going through the purpose of service keys, you said it has something to do with making sure that someone can replicate the structures without needing to see into the other encrypted bodies. I got that part? Okay. So this has a lot to do with where data storage block boundaries are, I guess, because you're worried about replicating with some model of blocks in mind, right?
Yeah, I think I'm following. Yeah.
Okay. Maybe that question was just a series of confirmations. Maybe that's it.
Yeah, it sounds like those confirmations are all yes. That's right. I mean, so the key, like, there's different layers that you can have with the body in particular, right? So in fact, buckets is an example which we can talk about later. That's like a practical use of what goes into the body. But in some cases, the body will be just a reference to like something stored on IPFS. And so really the thread, what goes into the thread is the accounting of like the order and structure of the body updates. But these could be, pretty arbitrary things and pretty opaque things as well.
So what happens if if some of the content inside of that body area, so it's encrypted to this key that's the purple dotted line here, what happens if that content is big, like multiple blocks, it's more than a megabyte, or it's some connected structure?
So we have users doing kind of both things. If it's big, then generally you just store like the CID reference to the big thing, and then you store the big thing in IPFS, and then it doesn't really matter. Just like any sort of blockchain thing, that's where you stick the CID there, you store the other thing somewhere else. And that's what buckets wraps that process up, basically.
Unless yeah, sorry, Carson, to interrupt. I was just going to say maybe a clear distinction is like blob data versus IPLD data. Because with buckets, there's no point in storing like file-like data, because you wouldn't, or at least for buckets, there's no resolution of blob-like data at this layer. But you could imagine some application having like a megabyte of application data that it does make sense to do like resolution on, or to actually track that state through time. But like for buckets, it's just files, so there's no like merging of files or something like that happens.
Okay. I guess
but I think to answer your question directly, it's up to the application to decide how that body is split
and how it's persisted.
Yeah.
So I guess the clarification I'm looking for is if you have the replication key, aka the service key, you're giving that to somebody because you want them to be able to confidently replicate the thread and all of its component blocks of data. And then if there's any complex, large or multi-block structure that's inside of that body region, then that is a separate responsibility to figure out how that's persisted.
Yeah.
Okay,
exactly.
Cool. Yep, that makes sense. That is a reasonable boundary.
I don't know if you mentioned earlier, Carson, you probably did, but just to clarify, a thread is technically a group of these single writer logs. So just to clarify that, I might have been the only one that didn't hear you say that.
I use the term set, but yes,
Set.
yes, yes.
That's more accurate.
Well,
yeah,
you're using DAG Koze for this, are you, for the encryption, or what are you standardizing your block format on?
Well, that's a great question. That's what Sander can answer because there's multiple levels.
Oh,
yeah. So right now, back when we did this originally, there wasn't that around. So it's done in kind of a crude way. We basically just symmetrically encrypt each. So each, like the body gets encrypted symmetrically. So that key there is just a basic symmetric encryption key, and the same with the read key and the replicator key. But that's something we'd love to improve on, is figuring out the right way, and maybe that's something that we can use like IPLD prime codecs for, because it's really cumbersome to traverse a log. Like you need to have the right algorithm. You need to know how to do it, basically. And it's not self-describing in any useful way. So that's something we've wanted to do for a long time. We just haven't had the bandwidth to tackle, like, okay, what's really the right best practice way to do the log encryption. And maybe there's something that we can come up with that it's sort of like from the IPLD team, like a best practice around doing this kind of multi-layer encryption, using codecs that other peers can understand in a pluggable way. I think that's probably available now. It's something we hadn't dived into. Another thing worth mentioning, so what Carson said at the beginning about threads being kind of a multi-layer setup, where what we're talking about now is like logs and the orchestration of records and logs between peers. Really kind of like our initial motivation for doing this might be easier to understand from the top, which is building a MongoDB-like interface to a peer-to-peer database. Because that's just one thing we've found in working with folks that are trying to build on like emerging Web3 stacks. They really just want an API that they understand. Something like Mongo is people love. So we were trying to kind of emulate that. And that's where we landed on this log-based sort of event sourcing architecture, where a thread is basically, it's a collection of these logs that represent, if you combine the tips of all those, they represent some state that can be resolved into a document in a collection. So it could be like, you can imagine a to-do app or something where one to-do is a document from one log, or maybe collaborated on via multiple logs. So that the way that those logs are resolved into some state is left at a higher layer, which Carson mentioned earlier. And in our ThreadDB setup, we call that the collection, or a collection instance. And that's where the kind of the parallels to MongoDB start. So that's sort of like if that helps with some context and motivation around this.
Dean, did you have a question?
Yeah, well, it's something like, just like trying to formulate it a little better, thinking off of what Eric had mentioned, which is, do users tend to stick with small amounts of data in the body or like, because I assume it just becomes like much more complicated when you can't just send the replicator key and the thread ID and say, please replicate this for me, because now you also have to replicate all this like manifest of extra data which lives somewhere else.
Yeah. Yeah, I mean, most people just interact with the database layer, which is JSON based. So they really can't put anything more than like JSON application data into these bodies. So yeah, I'm less than a megabyte for sure is typically the common use case. We have some, like, one of our heavy users is Anytype, and they have their own sort of database kind of layer that is based on a CRDT, because the one that comes out of the box with Threads is just, it's based on JSON patch. And it's pretty naive in how it handles conflicts. And so for them, they plugged in a different layer there. But yeah, it's a similar thing. Small data goes in the thread. Buckets is an abstraction that handles pinning, essentially, like for blob type data.
So do the buckets, can they, in the buckets world, does the replicator see the keys so that they can replicate that data?
They see the replicator key and the read key, because they have to be able to actually track the state. But we don't really have that concept of like replicate a bucket in that sense. Buckets are more like you can add a pinning service to a bucket, or you and I could share a bucket, but we haven't sort of extracted the replicator functionality into the bucket world, because yeah, you do need to see the read key to properly pin the bucket.
So there's no, these are not thought of as like complete DAGs. Like they have leaves that may be unresolvable, whether that's in a bucket or something else that's within that body. So I guess we ought not to try and think too much about these things as complete sets from a root all the way down to the leaves. It's just, there's a boundary, like a discrete boundary, where you hop out of this and the resolution is your responsibility at the API layer or something like that.
Yeah, exactly. I mean, we want to get to what you're describing. That was sort of the initial thing that we wanted to build. Though we had to come up with this like encryption scheme that just because there wasn't really anything out there.
Yeah, I would say, just to jump on that, it was the boundary is more practical than like theoretical.
Yeah, if it was some codec based thing that other peers could understand, they could traverse, they don't have to be like a specific thread peer, that would be amazing. We've even chatted a lot about making buckets less of a like a file based API, and making it understand just generic IPLD nodes. Right now, it's based on the Unix FS API. So a bucket, yeah, if you're manipulating the DAG that's describing a Unix FS structure or some other file structure, whatever you want it to be, it would be really nice if that was like more part of the body, and then you could be more specific about what you wanted your replicator to replicate. So it would handle like the whole pinning if you wanted to, as well as the replication of the thread. So it'd be kind of more of a native thing instead of these two different responsibilities. But yeah, I mean, just for context there, we found that that was the thing that most people really just wanted, like a really easy to use, immutable file system that you can sync peer-to-peer. And we just kind of, in some ways, kludged together some things we had to make that possible. But yeah, the vision is more of like a full DAG thing. That's helpful.
Yeah,
The,
makes sense.
the graph, the complete graph thing and encryption, that seems to be the bit where whenever we tried to come up to encryption, that's the bit that just makes it so complicated that it's hard to get over that line. How do you do that well? Where do you wrap them? Where do you expose them? How do you permission them? All that sort of stuff does seem to be one of the harder problems here.
Although
Yeah.
most of the complexity arises from like the fact that you don't know what the application developer requires up front, right? Like if there's a restricted subset that you know the application developer needs, then this problem becomes much easier.
Right. Yeah, and that's kind of where we've come at it from. I mean, it's hard to balance what you really want it to look like, you know, and then what your immediate users are asking for. And if they're not asking for the things that you really want to build, it becomes harder to justify building them.
So I might be interested in hearing some more about, you said that you're letting folks and you're seeing folks actually do the construction of their own conflict resolution algorithms on top of this thread structure. I would love to hear just any lessons learned you have at all from just like, how is that going? That seems like a wild place to be letting code breed.
Yeah. Well, to my knowledge, I think it's just any type, unless you know of others, Carson.
So it's pretty much just any type that's doing it like at this
Any
layer.
real level.
Yeah. In the DB layer that we also, like the DB API, we also have the concept of a codec, a pluggable codec that you can use. And there are a few teams that have done that. And then I believe Fleek has actually done some like document CRDT implementation on top, but that's a little bit different because that's more like, that's like even a layer removed. They just sort of like ship data around and then all the CRDT stuff happens like in the browsers kind of separately because there's already pre-baked libraries for doing that stuff. So it's really, they just use threads as like the distribution mechanism. You know, I'm probably botching exactly what it is that they're doing, but it's sort of a layer removed. But any type is the one that's doing the sort of like closest to the metal CRDT stuff that we know of. And then our CRDT is like an OT kind of inspired CRDT for the DB API. And you know, every sprint we like put off, develop more awesome CRDT implementation, which is, you know, the nature of the thing. But we've done some preliminary research to do like sort of opaque CRDT operations, which has been pretty promising, but just never gotten around to putting it into production. And that's like fully IPLD based CRDT, takes advantage of the hash structure kind of stuff.
Any type is a special case because they have at this point contributed like as much as we have been in the past 6 months to threads, to all layers of it, like the orchestration between peers and performance enhancements. And so they're like essentially on our team, you know. But I think probably for folks to really dive in and develop their own conflict resolution mechanisms, that's kind of the avenue you'd have to take because we don't really publicize or have any documentation on like really how to do that. I mean, that was the idea to begin with, but yeah, again,
Yeah, I mean, just basically most people just, it's funny because we built threads to be this like, higher level protocol to communicate data set updates between peers. And then we built the reference implementation of a database on top of it because that's what we kind of knew people wanted. And people are like, okay, cool, this database is all that I really want. So I'm never gonna go any lower than that, which is great. And we thought, okay, cool, you can run that on all your different peers all over the place. And they're like, well, actually it'd be better if you just ran it for us. So then, we're like, okay, we'll have the hub and we have this like database API. And now like a big chunk of our users are using like the gateway to interact with threads on a remote API. And, then it's like a centralized system with a bunch of like decentralized stuff underneath. The beauty of that, of course, is that if they change their mind at any time, they can just go off to the races and keep going, and that's important. But the easier we make, sort of the more we abstract on the thing that we built, the more people just want to use the abstraction. So that's why I think it's been fairly unpopular to build your own codec.
I think it also helps that like when you build the thing on top of the first thing, you also know more about how the first thing works than when you wrote it, which means like some of it is nicer and easier to work with because it's the abstraction layer, and some of it's just because you understand the bottom layer more than you did last time.
Yeah,
for sure. Yeah. And that's the sort of situation Anytype is in now too, which is they probably understand the Threads protocol as well or better than we do.
yeah, they've pushed it more than we have actually, and are finding sort of just areas to improve around orchestration mostly, like grouping updates by peer, and they've done a lot of that kind of work already, batching updates, and just pushing like basically pushing how much throughput you can get through a particular peer.
They've actually done some really interesting
Prioritizing
stuff.
updates.
Oops, sorry, Sandra.
Yeah.
They did some interesting stuff around like tracking thread heads. That's sort of like hash based, so you can see right away if you're in sync with other peers in a given thread or not, and decide very quickly if you need to request an update from another peer and that sort of thing. That's been pretty exciting.
Yeah, no, I mean,
sorry,
go ahead, Rod.
I was just wondering if we could talk. We don't have to do it now, but I was interested to shift to the view materialization side and the practicalities and performance and whether you do caching, all that sort of stuff. Where does that sit? How does it work? That seems like an interesting part of this, because it does seem like, over time, these things are going to get big and messy. How do you deal with that complexity over time?
I can take I'll say something and then Sandra, you can correct. So yeah, this is an interesting thing. Basically, caching definitely. In fact, in our reference implementation, peers basically just are constantly materializing the view on every update and keeping a reference state, and only rarely would actually rebuild the whole history, just for performance reasons. Ideally, and in the white paper, we have this mention of snapshots, so that you would actually snapshot the state at some like deterministic interval that all the peers in the thread would effectively be like agree on, so that they'd all arrive at the same snapshot at the same time. And we haven't implemented that because the caching that all the peers are doing effectively is giving that to us. But that would be like more useful, because that would, or like a true snapshotting framework would be useful, because then peers could basically hydrate from some like previously snapshot state, having never interacted with the thread before. And then that's a lot nicer for things like constrained environments like browsers, where keeping around 6 months of updates is probably not even possible. because your browser cache might just drop it. So these sort of like hostile environments are a little bit more they benefit from the snapshotting sort of stuff. And so we wrote about that in the white paper, but we haven't implemented that.
That's cool, because I feel like that's mostly where people in like CRDT land tend to like either figure it out or fall over, is that if you don't start garbage collecting your 8-month-old updates, then like things just like stop working.
Right.
No, it's totally doable though, right? In Threads, if you have like an ACL of all the peers, and over some period of time, some fraction of the peers sign off on the update, and you can tell that because they have all the hashes that point in the right places, right?
Yeah.
Like it's very doable. It just takes time to do these things.
Right.
It's hard to do them right.
Yeah, I think actually, well, we have started kind of more formal development with AnyType, and that's one thing that they're going to kick off is like a multi-sig way of doing snapshots.
And then to pile onto that, you can use that opportunity to do key rotation and other things that require consensus on the thread.
Yeah,
you're really bumping up against just basically a blockchain at that point, where you have to have consensus of a snapshot at a particular point in time.
Yeah.
Sort of.
right.
Although there are cheat codes though that get you around the consensus, right? Because you can just say like, here is the fork. You are allowed to follow the fork at your leisure, right?
Yeah.
You can see how many people follow the fork, right?
Yeah, absolutely. That was sort of our initial idea for how to do this kind of thing. Is this, just continually fork, have an ACL that's immutable, that's tied to the thread ID. And if you want to make modifications to that, you just fork it in thread ID that people can follow. It has new rules. But that has its downsides too. Like it's annoying to have to track multiple things.
There's some cheat codes on top of that even, which is like on a thread, you can have a fork without necessarily changing the thread ID, because really all you need for a fork is like a new set of keys. And so what you can have is you can have a group of people who are like, okay, we're going to use these keys now. And anybody else who doesn't agree with using those keys can keep trying to write to the thread, but we'll all reject those updates and you won't be able to read our updates. So, and so you can kind of like emulate that thread forking that way as well. So
just to mention a bit specifics around like view materialization, the way it currently works. So the materialization happens at the app layer, we call it, in the code base. A thread can have an app connected to it so that as logs come in, as records come in on a log or new logs arrive, the validation can be pushed up to the app layer, and the app layer can, based on rules that it has, it can decide like, is this permissible? And if yes, then it will handle the materialization. So there's kind of this like bi-directional bridge between the app layer and the networking layer. And when the app layer decides, okay, this is the new state, we're just dumping that JSON. It's all JSON at the app layer. And we're just dumping that into a Go data store. And then it can be read just from like a Mongo feeling API.
And just to clarify, currently there is no means by which you can join a thread and not have to catch up from the beginning of it. So currently, if you're connecting to a thread, you have to replay the whole lot to get up to the
Yeah.
Yeah, actually, so that's another reason why a lot of folks use like the hub or some other like running peer, is that they can have sort of like semi-participating peers. So you have a web app that queries the hub for like the current state, but then
Right.
adds like pushes updates to that state. It's to avoid that exactly.
Right, which is I mean, again, it's the blockchain one. You've got the light nodes and the full nodes.
100%, exactly.
Yeah.
Yeah.
Okay, that's fair enough. It does sound like a hard problem to solve, but certainly not unsolvable.
Right.
And
Yeah,
how big practically are these getting? Like, are people building really massive data sets on this, using this?
Yeah, so, well, again, Fleek and Anytype are our biggest users. So the way that Anytype model, they have Anytype, if you're not familiar, is like a Notion-based app or Notion style app. So the way they've modeled it is that each database in Notion speak, or each page has its own thread. So any updates that happen there go into that thread. So you can imagine, thousands of edits easily happening, and people can have hundreds. And I think they even said some folks have like thousands of threads. So these things the challenge quickly becomes pushing updates to peers, and that becomes like a very intensive, heavy lifting thing to do if you're always having to ask peers and receive updates in multiple threads. And especially in the multi-tenant setup, it becomes really cumbersome. So that's something we've started scoping, like how to break up a multi-tenant node into multiple, just like lots of different processes. Because
I guess. Sorry.
No, go ahead.
Just this question of organization. So I guess there is a choice at some point about how much you pack into a thread versus having separate threads. Like you could manage, like Anytype could manage everything presumably in one thread, just update everything in these massive documents. But then they have to have thousands of threads going. Is there any sense in nesting threads? Can you track threads within threads, or do you have a better mechanism for tracking the number of threads that, like, or does that just become an application concern where it depends on how flexible you want to be?
I think it always comes down to the fact that there's no like privacy. So a thread is, if you have the keys for a thread, then you have the keys for a thread. So usually the application decision is around like, what things do I want to be able to share, and what things do I want to keep private. So if you just had one thread for every user and they're putting all their stuff in there, then either it's public or it's private, so it becomes like, how do you build something where you can on Notion create a little page and share just a section of that page, or and folks always want like, they want to do the Google Docs style, like share with specific people or share a link, only people with access to the link, and that kind of thing. So yeah, I wish, I think there are ways to make threads more flexible so they can handle, they don't have to be so, well, I guess to back up. So there's two ways to handle this. You make a thread with a more granular ACL, and then you have to deal with like key rotation more frequently, or you just make it cheap to have a thread. And that's kind of the avenue we're exploring now. So like, there's no reason that you can't have 1,000,000 threads on a node. And that comes more down to like, how expensive is it to keep a thread up to date, and how expensive is it to basically orchestrate the logs. So that's kind of what our immediate goal is around scaling these things, is to make it so that you don't care how many threads you have. Like, you're not moving up against some machine boundary like your CPU or resource boundary with the number of threads you have.
Yeah. Because realistically, a thread is a set of keys, right? Like
Yeah.
there's not much more to track than that. A set of keys and some like tracking around like pure addresses and stuff. But it's like to have another thread that's that's referencing a lot of the same data is like basically the cost of creating a couple random keys. So then the expensiveness becomes just orchestrating those. And if you can do that in an intelligent way, which you can do with threads, because you have a lot of, like you have a network, a social network that you're of peers that you're interacting with. So you can take advantage of that in your like dissemination and sync algorithms. Then it becomes a lot cheaper to just be like, oh yeah, just to make it a thread. If you want to scope something to a key, just make it a thread.
Yeah.
And that's sort of where we're trying to lean to, kind of moving forward, I think.
These sort of architectural choices about where you divide things, how you structure things, does that end up being a problem for users? Do you end up having to deal with a lot of those sort of architectural questions about how they structure their use of these things, or did you find it's obvious for a lot of use cases?
I think that is a very good question. I think, most of our users interact with threads via the database API. And then their questions are like, how do I structure my data? Like, they'd be the same questions you'd ask of a MongoDB, like, how many collections should I have? What should those collections look like? Can I reference one collection type and another collection type? Like those types of architectural questions. We don't get the, like, how should I use threads, the protocol questions as often, because we don't have as many users interacting at that level. But we do have folks like Anytype, and they came back to us and basically said, we're using threads like this. It would be swell if it was even easier for us to use threads like this. And we looked at that and said, yeah, that's a good idea. We should try to do that. So, it's like a difference of where people are coming in. But for the most part, with like our JavaScript SDKs and the questions I field the most, it's like someone who works for MongoDB would answer the same sets of questions. Maybe a little bit differently because we're talking about a distributed system, but then, we try to do things like, okay, well, right now a thread is like not that cheap. So you might want to put like more collections into your thread, or you might want to like have one user be responsible for these collections and one user do some of that. But at the end of the day, it's more about how do I structure my database for my application than how do I optimize threads.
Are people more concerned about like the depth of the thread or like the throughput through the thread?
That's an interesting question.
It might be the same, because if you have high throughput and you leave it for a little while, then it's really deep. But
yeah, I think that's right. Yeah, I think they're both one and the same. The snapshotting thing is definitely a bit of a blocker for us at the moment. Just seeing like, yeah, for folks to really open up their floodgates.
And this is separate from, is this a bigger problem or the same or a different problem from I'm trying to run so many threads at once?
Well, I think they're separate actually, because the latter one is more about the fact that the bulk of the orchestration is thread based. So it tries to sync a thread versus trying to sync updates between peers that you share threads with, if that makes sense. We've done some work in that direction already. So like batching updates per peer that you're talking to across threads, and like queuing and all that kind of stuff that you can imagine as improvements. But currently it's still kind of bound to like a thread. So that's where some of the expensiveness of having multiple threads comes from, because it just, each thread adds some multiplier to like how chattery your node is, regardless of, in some ways, how many peers are in those threads. So yeah, it should be that it's just more expensive to communicate with more peers versus like how many threads do you have, you know? Kind of obvious in hindsight, but that was our initial implementation.
Yeah, I mean, it is an implementation detail versus a like actual problem.
Right.
But it's easy to say that.
Right.
I have a couple more things. I know we're running up against time here. There's a couple more things I wanted to cover, and I want to make sure that others, including Michael now, have their chance as well. One is we haven't really touched on buckets very much, and I just don't have any. I don't have much of a mental mapping of buckets at all, other than this is a UnixFS representation. Like this is a UnixFS materialization of a large collection. What is their relationship to threads? Are you storing like tag PB in these things, or are you doing something else where you can materialize a UnixFS out of the thread model, or like what is the relationship? What exactly are buckets, and what is their relationship to threads?
Yeah, so a bucket is built on threads in that the root of its UnixFS DAG is tracked in a thread, and that's really where it ends. Except for you get the replication piece, minus the pinning of that thread. The history of the changes in the bucket can be replicated using the thread structure. But other than that, you can imagine building buckets without the thread history tracking. Because the schema for a bucket is just basically a single entry plus some metadata. Like we track metadata about paths in a bucket. Like you can add whatever application metadata to a path. The encryption keys. So that's another thing. So it's Unix, just talking about buckets specifically, it's a UnixFS DAG that has built-in encryption, can do path-based encryption. It's full node encryption, so we're encrypting every node in that DAG, UnixFS DAG. It's multi-key, so like I could share with you one file in a UnixFS DAG, and you'd be able to encrypt down through that structure and encrypt the file, the leaf that I'm trying to share with you. There's an ACL built into it. It's also part of its thread schema. So it's just kind of like sugar on top of UnixFS is basically what a bucket is. And then just to recap, like its relationship to a thread is the schema is tracked in the thread, which enables like the syncing of a bucket, basically. So if Carson and I were sharing a bucket peer-to-peer, then I would receive updates via threads of changes that he made in that bucket, via just the hash changing or the metadata about paths changing. If I want to actually get those files, I have to pull it from IPFS network. So the bucket daemon handles the pinning at the file level. And then yeah, other things about buckets, like we expose an IPNS key that lets you find the latest version. We have we built a pinning API that lets you interact with a bucket over the standard pinning spec. So yeah, again, it's just like sugar on top of Unix FS, basically. People who are familiar with S3 or other like object storage, just things that they want like immediately when they start using Unix FS.
Right. So it's basically a Unix FS value added for all the things that people want in practical use.
Exactly. Yeah.
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 And the other thing I just wanted to quickly touch on was your roadmap or your sense of what the priorities are for development of threads. It sounds like snapshotting is important there. Like, do you have other things that that feel pressing to work on?
Yeah. So we're actually today and tomorrow doing a bit of road mapping and planning around threads internally, just to try and figure out where it fits in our stack going forward. One thing we've talked about is just severing off the database layer and focusing more on the network layer, because what we always run into are people asking for kind of like complex database things, like, hey, how can I do custom indexing? Like, we provide a very basic indexing mechanism, but if people want to do custom or compound indexes or like aggregators or any kind of like complex database thing that are baked into something like Postgres that's had decades of development, like we're never going to do that, practically speaking. So we think there's a way to back into that and maybe create connectors for more advanced databases by focusing at the networking layer more closely. So just this thread structure. That's one piece. Another piece is something we've touched on, which is like, how do you make having a thread inexpensive so that people don't have to worry about when they're designing their applications, they don't have to think like, okay, I only want to have 10 threads total per user and stuff like that. Just getting rid of that restriction. That's something we need for any type and some of the other heavy users. And then the last kind of main priority, well, I won't say the last, one of the other priorities is this multi-tenant setup so that people can use the replication piece of a thread more efficiently. And that's just sort of like basic breaking up of a thread node into multiple responsibilities. And then basically making the orchestration mechanism scale at a multi-tenant layer. And then I would say the last one that's on my mind, anyway, Carson can chime in too, but is redoing a bit of this encryption setup and trying to do it more in like a best practice IPLD way, given all the development that's gone on there since we initially did this. It would be amazing, and this is something that Carson and I have talked about, it would be amazing if there was just a library that you could use to do append-only logs on IPLD, and you could bake in encryption and like do these kind of like multi-layered encryption if you wanted to. I mean, basically, append-only log on IPLD is like a pretty easy thing. You just link roots together, right? But there are things that you want, at least we want, which is like this encryption layering. So if there was just some standalone library like that we could contribute, or that you all wrote that we could use, that would be an amazing thing to figure out and collaborate on. So yeah, those 4 or 5 things are kind of the main pieces.
Yeah, I mean, I'm definitely interested in leveraging some of the AES codex stuff that Michael did recently, and like taking advantage, just like kind of standardizing that whole thing a little bit more. And even though like single writer, like hash link logs are sort of like obvious, having a library which is like new log, insert record is pretty nice, like to have, and it would make would make building threads really easy, but would make other people who want to build similar things,
And there's
make it
also
easier for other things. Yeah. Anyway.
there's things that would be cool to standardize, like how many, do you backlink at a certain interval to allow for parallel traversal in intelligent ways? Are there ways to make verification of a log faster? Things like that. That would be cool, just to have it be like a standard sort of thing. A lot of our work internally now is focused more in like a Filecoin direction. So we're still, like, our hearts are still in threads, and we have heavy users that are using threads, and we want to eventually bridge the gap to Filecoin in some way, some hand wavy way that we've talked about a lot. But yeah, it just comes down to like division of resources and time.
So in terms of where we're heading in our interest here is that we're looking at this general problem of collections of data, and wanting to standardize something for the ecosystem. So how do we instantiate something that is a reasonable standard that serves a basic set of use cases? And you guys have done the most work in the ecosystem in creating something practical, and what we're trying to figure out is what are the base use cases that we care about, and what is the amount of complexity we can put up with to get that. And my hunch is that there's, with threads you're optimizing for a set of use cases that is perhaps a superset of what we're looking at, and so I'm trying to figure out what that difference is, what the delta is there, and is there something within threads, maybe a subset of threads that we could look at as extracting or standardizing on a piece of it, or does it actually require the whole lot? Like, so that's what we're thinking about at the moment. So I think we'd love to have more conversations about that topics. Yeah.
I have some other crazy stuff too.
And Michael's working on some more immediate term stuff as well, where he's interested in consuming, I think, threads for some stuff right now.
Yeah, or like they potentially solve some problems or parts of them, but I kind of need your input on a little bit first.
Very cool.
Happy to provide input.
So how much have you all looked at the ERC 721 spec, the NFT spec?
Not a lot of detail, but I know it exists and what it's for.
So a fair amount of things that people seem to think are insured by the protocol aren't. Like one big one is that like there is no guaranteed uniqueness anywhere. Like the uniqueness is of like a chain transaction that you can't actually predict. So if you're looking at an NFT or looking at NFT kind of like metadata or any of the assets, you can't go from that to an authenticatable structure. Like that's kind of one problem. There's like the only thing that really like tells you about an NFT is this token URI, which we have like now sort of pushed people to standardize on using IPFS URLs. And people were already doing this, right? Like, but now it's like really clear, like you need to do that. And the spec mentions like, maybe you want to point this at a metadata.json file that conforms to this particular schema, but there's a lot of people that don't do that. And then a few people that just break the entire spec, which is really annoying. But one of the things that I realized is that since that's an IPFS URL, and then that thing inside of it's a CID, we can effectively program it with new codecs And we can use new codecs to basically signal other features that we're doing inside of chains around NFTs, if that makes sense. So like one thing that we could do is we could create a spec for, say, like a mutable NFT, where the IPFS URL is to like a new codec that we identify, and then it's always a identity multi-hash that just has bytes in it. And so now that entire sort of prefix, right, all the way up to, but right before the length, is effectively the prefix for like a key value store almost, right, on the chain. Because you can look at any chain and you can go, okay, like who is the first person to do this particular identifier, right? And then that is effectively just like that key owner. And then the whole chain of custody for that key in that particular chain belongs there. And then you can just post messages to the NFT address in order to do updates. And you can even do things like, okay, only the owner is allowed to update, right? Like you can tool that kind of a thing in. But once you start getting into updates and having this like long running data structure that actually takes updates, like I start thinking about threads and some of the problems that threads do. I think that some of the differences here though, is that like you want to, well, one is that you want to actually leverage the existing ownership information in order to do permissioning. You don't want to like tool that outside of it. And you're also like not relying on any outside tooling, like any off-chain tooling for that either, which is kind of cool. But that changes like some of the ways that I think you might use threads. I don't know. Have you guys thought at all about like this weird space?
Yeah, I mean, this is exactly how DIDs, the Ether DID spec works. So you actually mutate a DID, a decentralized identifier document for a given like Ethereum address by posting to the address your different like updates, and then the events on that smart contract can then be queried and resolved to resolve the actual DID document. So you have a mutable document that you can change over time, and you could effectively make those updates like thread record updates basically, but they're native Ethereum events. So you can query for that, and it's pretty cool because it costs a lot right now to mutate that NFT or that DID document, but it's cheap to query it. And so it's great for DIDs because you resolve way more frequently than you update. Yeah, it's the same setup, I think.
I think that this becomes really interesting in like the context of NFTs, right? Because if you look at kind of what artists and different people are doing with them, they're like creating kind of these one-time assets, and then there's like the secondary market for selling them. But if you have one that's mutable and only the owner can mutate it, you can start to create like artistic works that go viral, and selling them as part of the virality and moving them around as part of the virality. And then because you have that contract for a percentage of every sale, that actually makes that much more profitable than like these big ticket sales, right? Like if you have something that really goes viral, you actually capture like a huge amount of value from that.
Yeah, totally.
A friend of mine worked on the Grimes NFT, and we've been talking about like a mixtape where like when you own it, you get to add your track to it, and people sort of follow these mixtapes when they get popular, and then that like leads to greater resale value. Yeah.
I had thought about that like last week around NFT resale, and I just kind of assumed that the percentage was baked in, like the artists can continue to make a little percentage of a sale, but maybe that's not the case. That's pretty unfortunate.
It's in the contract. You write it in the contract, so you have to define what it is.
Right.
And there's a de facto standard right now that like artists are taking, I think 10%. I think that's it. But you see other people that are like minting them, like putting themselves in these contracts. Of course, you see like sometimes artists don't have that in there, but I think that there's a lot of like cool stuff that you can do with that. You can spread out different payments of different percentages to different wallets and stuff. It costs more money to create it because there's more data going in, but if you want to get fancy with it, you can.
Yeah. Yeah, there's kind of a side discussion that we've had around threads for a while around a thread did, so that a thread peer can advertise services. And one of those services could be like a buckets API or whatever else you can imagine, like media encoding or something like that. But yeah, I don't know if that's worth. I don't want to go down another rabbit hole.
Yeah, I think one problem I've been tackling is like you have on-chain and off-chain data, right? And all of like, you know, if you parse the chain, you can take some of the chain state into the offline or into the off state, right? But when all you're passing around is the off-chain data references, you don't necessarily have a way to call that back and like authenticate it, right? And this like becomes a problem when you're building some of the more advanced workflows. So like one thing that I want to do like relatively soon is put out a spec for just an origin property in NFTs that points to the genesis block of the chain that it was minted on.
Mm.
So then if you ever get an NFT by address, you can always authenticate the entire chain of ownership for right now for that NFT. And you can actually carry around that context. Whereas right now, like you can literally just like make them like, and if somebody in a side chain like makes a really popular NFT, you can just mint it in Ethereum and then like definitely go sell it like it was that one, because people will assume that the Ethereum one is the real one because nobody's checking all the side chains to see if there's like an older version of that same NFT, right? Like these are like real problems.
Yeah.
That actually came up in a call I had earlier today. That exact sort of like, well, actually it was seen as a benefit, but also like a benefit that has very serious like
it's a benefit in that it makes moving them easier, right?
Mm-hmm.
Like if you want to move it, you can use the same address, but and then stamp the tombstone, right? In the old one, it points to the other chain. But like you have to know to go and authenticate it on that chain in order to do that lookup. And what you'll see is like, you know, once things get popular enough, people will just like try to steal them in the Ethereum chain unless there's like a solution to this problem. So, you know, if you're minting them in a side chain, like put the side chain in that property, and then, you know, anybody who wants to authenticate it will go through the side chain. If they transfer it to Ethereum, they'll see the transfer and then they'll go look at the Ethereum chain. Right? And if somebody tried to snipe it, you can just do it at a new URI.
Yeah, super cool. I think one thing that we've been missing from Threads is just like a clear use cases, you know, that we can really rally, because you can imagine doing things differently. Like if I were to design this for IoT or something, or design it for NFT tracking, or so there's been a like slight paralysis around some decisions, just like without super clear use cases, you know. And right now we're just mostly driven by our heavy users. But yeah, that would be, I mean, yeah, it'd be great. We could chat about some more of those NFT ideas, or I'd love to hear if you guys had things you could point us to around your collection stuff, and we could read about that. And
well, we're working on the basics of what it is we're even talking about right now. So I think maybe in the next conversation with you would be simply about the use cases that we are thinking as important, and then looking at the intersection of those with what you have, and then like that because that, and then that should make things obvious for all of us. Really, that's the next step for us is there's outlining those use cases that we think are important. And
yeah, that would be great. I mean, and then there's some sort of intersection of work there then that we may be able to pick as a standard that we adopt and then build stuff on top of, and that would be really interesting.
The way it was put recently was that the notion of collections of data, particularly IPLD collections of things, was something that was punted early on in the IPFS design process and never really got back to. And it's taken people like you to come up with ways of solving that. And it really would be good to have something that was advertised as a standard. This is how we recommend you do this, and then we have interchange discussions about how you can talk to different services using these things, and how you can bake them into all sorts of other things like Filecoin. How you can build them into DAOs, data DAOs, all that sort of stuff. There's a whole range of things where if you have a single means of defining a collection of things, then you can unlock a lot of power. So that's what we're thinking.
I mean, it's the same thing as we were talking about with DIDs, right? It's like, if you've got some sort of definition of what a collection is, then you can implement that on Ethereum. And you can implement it in just hash links, IPFS CIDs, and you can do it on Filecoin. You can do it everywhere. Yep. And that's pretty exciting.
For how much we use CIDs, there's been like a substantial lack of development in even like some of the more basic questions, like what is the smallest representation of a bunch of CIDs? What is like a good multi-block data structure for storing a large collection of CIDs? Because like the mutation rate's just horrendous, right? Yeah, and I don't think that we've gotten very far. Like other than in that ZDAG spec that I wrote, there is a compression algorithm for CIDs that just leverages ordering in order to get rid of the prefixes and some other stuff. So like you can shave like 15% off of the size of just like a bunch of CIDs. But other than that, like I don't even know what and that would be a new codec, but.
Okay, well, Adine, have you got any other questions that you want covered before we?
I guess just briefly on the networking side of things. Yeah, if you need stuff, you want to talk through things, I'm available. I have not forgotten our conversation about trying to publish many IPNS records with buckets. I should have some nice surprises for you soon. And yeah, I too feel the pains of I would love to work on the cool mutability thing, but there are all these immutable things that need to get taken care of first. So if at any point that's something you guys are brainstorming, I would love to be able to listen in.
Yeah, and we've started to do a little test ground work with Anytype, just to basically test little improvements that they've been making. And we'd love to just like throw, Gossip Pub in there and be able to, ideally we could like play with little variations on Gossip Pub here and there, and just like see these things run at scale.
You
really
should be
easily.
able to in test ground, because I know like there was a group of folks who were doing a bunch of testing in test ground with a lot of gossip, especially in the months leading up to Filecoin launch, to be like, if we hammer this and we try and be really mean about this, will the network still hold up okay? And they did fine. So you should be able to test those things larger. One thing that is sort of interesting is that as it stands right now, Gossip Sub has a maximum number of topics that a node is able to tell you that it cares about. And so if you're running a single node that's trying to listen on 1 million topics and the maximum message size is like a few megs, you're going to start getting real sad, right?
Right. And that comes in with like this multi-tenant stuff, where you have these replicators, and that's really where we see the problems there. And we don't want to just like have to keep pumping money into the cloud provider,
and
like 100 gig memory machines.
Right. Especially because you don't really need the 100 gig memory. Boxes are square, and what you really need is a whole lot of CPU, right?
Yeah.
So we can talk about ways to do some like horizontal scaling here, and also, I mean, if we really wanted to, we could find ways to expand the number of like modify Gossip Sub to be able to handle more topics, more subscriptions. But it feels like there's probably some good ways to do horizontal scaling here, and it may be like a the protocol is warning you, like, before you go on, let us think if there's another way to do this.
Yeah.
And so, yeah, if you guys want to go, brainstorm some options, we can definitely talk through those.
That's great.
Awesome.
Probably wrap it up. Thanks so much for your time, but I think we'll come asking for some more of your time in the near future.
Cool.
It's been fascinating.
Yeah.
I mean, this is something Sandra and I have been wanting to do for a while anyway. It's just a little bit more outreach around threads and seeing where the like sort of standardization points are. So this is great. It's good timing too.
Hopefully
Excellent.
it was useful and we weren't too like rambly or answering
No,
questions.
it's good. I've appreciated the free form format here because like looking at documentation is one thing because it's often user focused, and then the white paper it's got this academic thing about it that leaves me wanting just very specific details. So
Yeah.
having free form is really helpful. Yeah.
Cool.
Great. Okay.
All right. Thanks, everybody.
Thank you. I'm going
Thanks
to
all.
end this. How do I stop? There we go. Stopping the live stream. Bye.